Okay, and of course, there are many variations of this combination. First of all, there are many variations of line search methods, right? And I'm not going to discuss any particular one of them, but like there are a collection of heuristic methods that searches within this one-dimensional line, right? You can think about, for example, performing a bisection kind of approach. You always chop the line into two segments and look at, okay, is the half point small enough? If not, further cut it to half, etc. So a lot of variations in line search. There are also a lot of variations in the method of what we call the quasi-Newton method. So the variation of quasi-Newton, they are basically different methods of approximate the most expensive part of this computation, approximate the second derivative of the objective function. Okay, so there are schemes that uses a series of gradients to do finite difference approximations to get the an approximation of the Hessing, for example. That's one of the most popular quasi-Newton methods out there to use. Well, there could be even a steepest descent. Steepest descent actually is very popular in the recent rise of machine learning methods. That is to basically take the simplest approximation of the Hessing. That is approximating it with an identity matrix. So if you approximate the Hessing with identity matrix and you look at what algorithm that leads to it, basically my delta S is going to be minus of the gradient. So that's why it's called the steepest descent, because I'm just following the gradient direction, and it heavily relies on the line search to actually take a good step size, because without the Hessing, you no longer have any idea of how big of a step is appropriate to take. All right. Okay, so this is a general overview of what we call unconstrained optimization methods. So and one of the very important things in engineering is constraints when dealing with a lot of the optimization problems. If you want to optimize an airplane for example, maximum range or maximum fuel efficiency, it's quite common you have a myriad of constraints. For example, you have to take off and land. So the takeoff runway length and the landing runway length is actually a pretty obvious constraint, right? And you have many other constraints. So the optimization of under constraint can be formulated as the minimization of a same kind of a objective function, right? I mean, if it's maximizing another different function, you can just formulate it as minimization of the negative of that function, right? So usually we can just write as minimization, such that a constraint can write as G of S, it's satisfied. So another general nonlinear function is equal to 0. Again, we want to discuss this starting from the simplest case, is how do we optimize a quadratic under a linear constraint. So we can no longer optimize actually a univariate quadratic, because if you have a linear constraint on a univariate function, you already uniquely determined what S is, right? So if S is one-dimensional and you have a linear G, then, well, we are already done. There is nothing to optimize. the constraint uniquely determines the S. So we want to have at least 2 S's. So let's consider the simplest constraint optimization case. We have S1 and S2 being 2 independent variables. We have the same kind of a quadratic as we had previously. So if you draw the contour of J, it's like this. Okay, now let's focus on the new stuff. That's the constraint G. So G being a linear function, right? Let's write it down a little bit more. So G of S being a linear function has to be that, so let's just write D transpose S plus E is equal to 0. So that's a linear constraint, right? And which means D1 S1 plus D2 S2 plus E is equal to 0. So I have a linear combination of S1 and S2 that's equal to minus E, a set value. How do you visualize that in the plane of S1 and S2? Well, if you have a linear combination of S1 and S2 equal to a set value, that means I have actually constrained S1 and S2 on the line, like that. So that's going to be where G is equal to 0.